Welcome back, everyone, for another deep dive. Today we are diving into the OEIS, the Online Encyclopedia of Integer Sequences.
Yeah.
It's a huge resource, a huge catalog of these
Yes.
mathematical sequences.
Yeah.
And, anyone listening, especially anyone studying number theory, this is an indispensable resource, right?
It really is.
So we're going to dive into one specific entry, and it's a doozy.
Yeah.
It's A000186.
Okay.
And the sequence concerns these things called 3x n Latin rectangles with an ordered first row.
Yeah.
And that might sound like a mouthful.
Mm.
So let's unpack that a little bit.
Yeah, let's take it one step at a time.
So what is a Latin rectangle?
So you think of a grid
Yeah.
or an array, and it has a certain number of rows and columns. So it's n by k, so n rows and k columns.
Okay.
And you fill in the grid with the integers from 1 to n.
Okay.
The crucial rule is that you cannot have the same number appearing twice in any one row or column. So each number from 1 to n appears at most once in each row and each column.
Okay, so it's kind of like a Sudoku puzzle.
Yeah, it's a bit like a Sudoku.
But not necessarily square and
Right, so-
without the block constraints.
That's right. You just have the row and column uniqueness.
Okay, all right. So A000186 deals with 3xn, Latin rectangles.
Yeah.
What's the 3 by?
Yeah, so the 3 by part tells you that there are 3 rows in your Latin rectangle.
Oh, okay.
And the n represents the number of columns. And as this number of columns changes, you get different terms in the sequence A000186. So we're looking at these rectangles with 3 rows and a varying number of columns, n,
Okay.
filled with numbers from 1 to n,
Right.
such that this Latin property, no repetitions in rows or columns.
Right. 3 rows and columns.
Yeah.
Numbers 1 to n, no repeats.
Yeah.
And then you said ordered first row.
Oh, yeah.
What's that about?
So that means that in the very first row of our 3 by n Latin rectangle, it's not just any random arrangement of the numbers from 1 to n.
Okay.
It's specifically the sequence 1, 2, 3, and so on, up to n in increasing order. So that's a restriction that we impose, and that gives us what's often referred to as a reduced Latin rectangle.
So we're essentially starting with row 1 fix.
Yeah.
And then, we're seeing how many ways can we complete the other 2 rows.
Yeah. And this sort of feels like it fits into a bigger area of math, combinatorics.
Yeah.
Yeah, absolutely.
What is combinatorics?
Combinatorics is the study of counting and arranging discrete objects.
Oh.
So, and enumerating these specific 3 by n Latin rectangles with ordered first row is a particular problem within that broader study of counting combinatorial structures. Yeah, we're trying to find a way to determine exactly or approximately how many such arrangements are possible for a given value of n.
So, for this deep dive, our goal is to understand what mathematical research has revealed about the number of these very specific Latin rectangles.
Yes.
And I guess they use R3 of n sometimes, or?
So R3 of n is often used when the first row is ordered.
Okay.
L3 of n is when it's not ordered.
Oh, okay. So, all right, so what has the mathematical community discovered about counting these things?
Yeah, so the general problem of counting n by k Latin rectangles has a long history.
Okay.
And early on, McMahon
Okay.
was a mathematician who develops these powerful operational methods
Okay.
that could, in principle, solve this for any n and k. However, for our particular case, k equals 3,
Right.
people have sought more explicit and more usable solutions.
Okay.
And figures like Erdos and Kaplansky, among others, directly address this scenario.
So McMahon gave us like a theoretical framework,
Yeah.
but getting to the actual numbers when there's 3 rows
Yeah, it's
was
not quite difficult.
What were some of the initial challenges that researchers faced?
Yeah, so exact enumeration proved to be quite a hurdle early on.
Okay.
However, a very insightful conjecture arose, proposing that the total number of n by k Latin rectangles behaves like n factorial to the power of k multiplied by a factor of the exponential of minus k times k minus 1 over 2. So this gives us a sense of the sheer scale
Okay.
and the rapid growth in the number of these rectangles as n and k increase. It's like trying to count the possible shuffles of multiple decks of cards. The numbers get astronomical very quickly.
So asymptotic, this formula gives us an approximation for huge values of n.
Yeah, it describes the trend as n becomes very large.
Okay.
Now, there were some early missteps in trying to confirm this conjecture for k equals 3. A mathematician named Jacob made an error that initially led him to doubt the conjecture in this specific case.
Okay.
Fortunately, another mathematician, Karawala, corrected this error.
Okay.
And through extensive calculations,
Okay.
provided very strong numerical evidence supporting the conjecture for 3-row Latin rectangles. Now, interestingly, it appears that Riordan was the first to give a rigorous mathematical proof specifically for the k equals 3 case.
So the early picture involves a guess about the growth rate, some hiccups and corrections, and then a formal proof.
That's right.
For the 3-row case.
Yeah.
Where do Erdos and Kaplansky come in?
Yeah, so Erdos and Kaplansky's work was a significant step forward. They aimed to prove this asymptotic conjecture, not just for a fixed number of rows k as n grows infinitely large, but also for a range of k that could itself grow with n.
Okay.
Specifically up to roughly log n to the power of 3 over 2 minus epsilon, where epsilon's a small positive number.
Okay.
They also pointed out that for a fixed k, like our k equals 3, a shorter proof was indeed possible.
So they were trying to make it so that the rows could grow as n grows.
That's right. So not just fixed k, but k growing with n.
Okay.
Yeah.
Interesting. How did they tackle this?
Yeah, so their primary tool was something called the sieve method, which is also known as the principle of inclusion-exclusion.
Okay.
So imagine you want to count the elements in the union of several sets. You could first add up the sizes of all the sets, but then you've overcounted the elements that are in the intersection of 2 sets. So you have to subtract those, but then you've undercounted the elements that are in the intersection of 3 sets.
Right.
So you add those back in, and so on.
Okay.
Erdos and Kaplansky used this idea to estimate the number of ways to add a k plus 1th row to an existing k by n Latin rectangle without violating the Latin property.
So they're systematically getting rid of the
good ones. Exactly.
Okay.
They started with n factorial,
Okay.
the total number of permutations for the new row.
Right.
And then they subtracted the permutations that would create a conflict, a repeated number in a column with the existing k rows.
Okay.
In at least one column. Then they adjusted for the oversubtraction of cases with conflicts in 2 or more columns, and so on. And this led them to a formula, which I won't write down explicitly, but it involves this quantity A sub r, which represents the number of ways to choose r distinct integers in the existing k by n Latin rectangle, such that no 2 are in the same column.
Oh.
So that was their key idea.
So what were the key results they got?
So for the general case, where k is less than approximately log n to the power of 3 over 2 minus epsilon, they rigorously established the asymptotic formula for f of n, k, the number of n by k Latin rectangles as, well, it's n factorial to the power of k times the exponential of minus k times k minus 1 over 2.
Oh, okay.
So this confirmed that earlier conjecture over a much wider range of k than was previously known.
And what about for 3 by?
Yeah, so for the case f of n, 3, they derived an asymptotic series, which is a little bit complicated, but it's basically 1 minus 1 over n minus 1 over 2 and squared plus and so on. They even included a table in their paper comparing this asymptotic approximation with the exact values calculated by Karawala. And the agreement was quite good, especially for larger values of n. This kind of validation is crucial in asymptotic analysis.
Yeah. And did they have a sense?
Yeah, so they observed...
What's the limits of their method?
Yeah, they observed that the form of their asymptotic series seemed to suggest that their expression might become inaccurate. Perhaps even invalid, around k equals n to the power of 13. although they acknowledged they couldn't prove this rigorously.
So they pushed the boundaries of our understanding,
Yeah,
but they also
knew where the limits might be.
Okay, what came after their work?
Right. So a significant leap forward was made by Godsil and McKay, who were able to improve the range of K, for which we have accurate asymptotic enumerations of Latin rectangles.
Okay, what was their main result?
Yeah. So they proved that for n approaching infinity, and K equals little o of n to the power of 6/7, meaning K grows slower than n to the 6/7. The number of K by n Latin rectangles, denoted by elif K, n10, is asymptotically equal to this falling factorial to the power of K times the exponential of minus K choose 2.
Okay.
So it's worth noting that this was actually a consequence of a much more general theorem that they proved.
Okay.
But nevertheless, this gives a much larger range for K.
Right, it's huge.
Yeah, compared to Erdos and Kaplansky.
Yeah.
Yeah, so what were the key ideas behind their approach?
Yeah, how did they do it?
Well, they brought in graph theory. So they associated a bipartite graph with each K by n Latin rectangle. So imagine two sets of vertices, one representing the rows and the other representing the columns. An edge exists between a row vertex and a column vertex if the number appears in that cell of the Latin rectangle. So this gives you a K regular bipartite graph. Now the problem of extending the Latin rectangle to have K plus 1 rows becomes related to counting perfect matchings. In the complement of this bipartite graph, they show that this count can be expressed using an integral involving the root polynomial of the graph.
Wow, so they used graph theory to count these things.
That's right.
And so for 3...
So for K equals 3?
Rows, what did they find?
For K equals 3, they derived an asymptotic expansion, which is a little bit complicated, but it's basically the exponential of minus 3. Times 1 minus 3 over n plus 13 over 4n squared minus 203 over 36n cubed and so on. Okay.
And this is different than Erdos and Kaplansky's.
It is. It's a little bit different. Suggesting that it's perhaps more accurate.
Interesting. So we've talked about these asymptotic estimates for large n. What about exact formulas for R3 of n? Or RK of n?
There has been significant work on finding exact formulas as well, most notably by Peter Doyle, who developed a method that allows you, in principle, to generate an expression for the number of K-line Latin rectangles for any K.
That's huge.
Yeah, it's quite a powerful method.
How does it work?
So his approach is based on a generalization of Reiser's formula for derangements. So the derangement is a 2 by n Latin rectangle with an ordered first row. Where no number in the second row is in the same column as it was in the first row. Doyle focused on counting reduced Latin rectangles, where the first row is in the standard order. So that's RK of n. And then the total number of Latin rectangles, LK of n, is just n factorial times RK of n. So how does he achieve this? Well, he introduces this clever way to represent Latin rectangles using 0-1 valued tensors, which are these multidimensional arrays. He also uses a nice analogy of a Latin hotel with shafts, halls, and corridors to rephrase the conditions that define a Latin rectangle in a more combinatorial way. So each number appears exactly once in each row. At most once in each column. That translates into rules about how guests can be placed in the rooms of this hotel. So he uses this framework to derive the counting formulas. And he employs the principle of inclusion-exclusion. But rather than focusing on conflicts, he considers the set of omitted halls in his Latin hotel by carefully applying inclusion-exclusion based on which halls are omitted. He derives formulas for RK of n. And so for 3, he derives the formula for R3 of n. It's quite complicated. We'll write it down here. It involves these parameters. But it extends Reiser's result for derangements, the K equals 2 case, and provides a clear pathway for generalizing to taller rectangles.
So we have these asymptotic estimates and this method for finding exact formulas.
Yeah.
How does the OEIS
sequence
fit into this?
The OEIS sequence, A000186, is precisely the sequence that gives you the number of these 3 bi-n Latin rectangles with an ordered first row. So it corresponds to R3 of n.
Okay.
And represents that specific case, F of n, 3, or L of n, 3, that we've been discussing.
Okay.
And the OEIS just gives you the terms
of
this sequence, so it gives you the numbers.
And that comes from Doyle's formula?
In principle, yes.
Yeah.
But it's hard to compute.
Yeah, the complexity of the formula makes it very challenging.
Okay, so this seemingly simple problem has led to all this.
Yeah, it's quite remarkable.
Research, yeah. To recap.
What are the main takeaways?
So the enumeration of 3 by n Latin rectangles with an ordered first row. The sequence documented in OEIS A000186 is a beautiful example of a challenging combinatorial problem that's been tackled with a range of increasingly powerful mathematical tools.
Yeah.
And our understanding of these objects has deepened significantly over time. While exact formulas exist, the asymptotic results give crucial information about the growth rate as n becomes large. And the OEIS itself is a valuable resource for anyone interested in seeing the initial terms of the sequence.
So for anyone listening, if you want to dive deeper into this, what would you suggest?
Well, I would definitely recommend looking up the sequence A000186
to
see the initial terms and the references there. You could also investigate the related concept of Latin squares, where the number of rows equals the number of columns. Although that's an even more complex area.
Yeah.
And for those with a stronger mathematical background, you could delve into the techniques of asymptotic analysis and the applications of graph theory to combinatorial problems like this.
It's amazing to think that just arranging some numbers leads to this much
It's remarkable.
depth.
Really.
It makes me wonder, like, are there implications in other areas of math, like experimental design or coding theory? You know? I think we'll have to save that for another deep dive, though.
Yeah, I think so.
Well, thanks for joining me on this one.
Yeah, thanks for having me.
It was a lot of fun.
It was fun.
And we'll see everyone next time.
See you then.